My name is Rickard Sjögren. I work at CellVoyant as a project manager. I've been working for the past 10 years in the intersection between AI development and biotech industry, and for past 2 years at CellVoyant. So for those of you who are not familiar with CellVoyant, so we're a UK-based startup founded in 2021, an AI-based tech bio startup developing a platform to help cell therapy development, all the way from using AI to monitor how your cell therapy processing is doing to improving the processes and protocols. So I will give a very brief company overview, and then I will share some of the work that we have done with the trophoblast stem cells in collaboration with Accelerate Bio. So with that, let's start. So this is an overview of the challenges within the cell therapy industry, and I think that most of you are familiar with this. And it starts all the way from the donors, and I know that trophoblast stem cell has some advantages in how they source their materials, but it is a well-known challenge within the cell therapy industry that cell quality varies heavily, and that has all kinds of downstream effects. Then you go through the process of reprogramming your cells or some type of direct differentiation, but it all comes with the challenges of high costs, unpredictable results. You have few assays to test that you get. What you get is what you're supposed to get. Timelines are very long, as Seiko illustrated with the comparison with the BlueRock compared to TSC processes that can take days to multiple weeks or months to get the end target cells that you're interested in. And genetic instability is also one of the key challenges. And this is both in the clinical space as well as in the preclinical space. And these are the challenges that we are addressing in CellVoyant. So we are building our tech platform called FateView that I will introduce right now. So FateView is an AI platform combining label-free microscopy with AI to read out any kind of biological information from label-free data to not only read out what is now, but also forecasting into the future. And that gives us the information that you may need to not only understand how your cells are doing now, but you're also building towards forecasting into the future to guide you on how to modify your protocol on the fly, and to get the best end results. So this is a snapshot from a video of stem cells differentiating into endoderm, and we can detect the individual cells and determine what current state of they are in. Are they still very potent cells, or are they in an intermediate cell state, or have they reached the target cell fate? So as I mentioned, FateView is a platform combining live cell monitoring, and thanks to using AI, can reach the molecular depth of high content analysis. So there's a few different steps that, of course, you run your experiment, you are differentiating your cells, and you can acquire images using any label-free images using any microscope, really. And using FateView, we can first of all quantify biomarker expression. And I will come back to that, how we did that on the TSCs from Accelerate Bio. But you can then use AI to read out the current state of the cell culture from the label-free images and get an instant readout. Thanks to being a label-free experiment, it's very low effort and low cost and all of that. As I mentioned, we're all working on how to forecast the future culture state that, okay, based on how it looks now, how will it look at in the future? It allows us to either modify a protocol, can, for instance, terminate a protocol or experiment that seems to go in the wrong direction and start over. And the end result, of course, is to optimize the results that help you find how to adjust the protocol process in a multifactorial process improvement way. So the main focus of today is on quantifying biomarkers, but we will have a brief look into how you can use that information to optimize the protocol. And one of the key advantages of using live cell imaging and labor-free analysis is that it allows you to do real-time monitoring. So combining labor-free imaging and AI, we can get the molecular readout or time resolved thanks to that live cell imaging is non-destructive. And this is an example of where we used FateView to on iPSCs, differentiating towards ectoderm germline. And we could see that out of the 4 cell lines that we were differentiating, we could, using FateView, detect that one of the lines was completely incompetent within 48 hours, whereas this is a six-day protocol. The current standard is to do either flow cytometry or immunocytochemistry at the endpoint. And of course, then you're limited to the endpoint measurement, not allowing you to get intermediate insights. In this diagram, you can see the line is the FateView readout, and the dots are when we have done repeated immunofluorescence imaging to validate the results. You can see a very good correspondence between FateView and immunofluorescence. But now moving into the TSCs instead. So working with accelerated bioscience, we have been developing a FateView assay for to monitor TSC differentiation towards neural stem cells. And the process is a 2-phase process. That the first phase is basically setting up a custom assay. So we have our trophoblast stem cells. We see them, we induce differentiation, and then we acquire images. So in this first phase, we actually acquire both label-free images and immunofluorescence images. In this case, we're looking at Th1, so IF images of Th1, paired with the label-free images, and using this data, we can then train the FateView AI and then set it up to use in new experiments. But this is a one-time step that you do once, and then for the second phase where you want to use this assay, it's the same process. You have the cells, you induce differentiation, but then you only need to acquire label-free images, but can then instead use FateView to read out the biomarker that you're interested in. So in the case of TSCs, we were interested in Th1, so we can use the FateView to quantify the Th1 expression without doing flow cytometry, without doing IF imaging. Using this approach, we can quite reliably quantify Th1 in differentiating TSCs. So if we first validate FateView against immunofluorescence imaging, we see a good correspondence between the FateView Th1 expression and IF in untreated and treated cells. Of course, it's not perfect, but given that it's very challenging, TSCs are very delicate cells, and it's a subtle marker to detect, but we have good correspondence to compare things, which we can use then to compare, for instance, how efficient is differentiation between different cell lines. So here we have 3 different TSC cell lines, and we can use FateView to quantify how efficient was differentiation as measured by the FateView Th1 quantification. And we can see that one line had very good separation between treated and non-treated cells, indicating a high differentiation efficiency, whereas some lines we still had a good amount of undifferentiated cells in the treated condition. So you can use this as a very low effort assay to quantify either the effect of different protocols on your cell behavior, or comparing different cell lines, for example. And looking at a little bit in how you can use this information to guide protocol development, that you can vary the protocol in different ways and then use FateView to read out like your biomarker expression for the different treatments. For instance, each one over time here from actually starting at the end of differentiation, but we let it try to let it run for longer to see the results. But then you can actually relate the efficiency or yield to your experimental conditions. For instance, investigate what impact does varying the dose have, and or in relation to how long the differentiation, how long you let the differentiation go. And by using Fate, we enable them data-driven insights to reveal relationships between the protocol and the yield or efficiency. For example, this particular cell line, we could see that it preferred longer differentiation time and lower dose to drive higher TH1. But we could see a sweet spot in the dose that too high or too low reduces the expression. And especially when accounting for seeding density, we could see a stronger relationship. This is an example of the kinds of insights that can get, and we illustrated that using FateView, we can develop a labor-free assay to quantify differentiation efficiency into neural stem cells on TSCs. And with that, this is my last slide. So CellVoyant is an AI first technology partner based in Bristol, UK, and we are always on the search for collaborators interested in working with us on exciting cell types like the TSCs with Accelerate Bio. And if you are interested to learn more, please feel free to take a screenshot and reach out. Thank you.